Okay, so we're going to look at a bit more kinematic stuff today, specifically vectors being used with kinematics. Now, just to remind you, this word kinematics, when you see that word, what you can kind of think to yourself is Suvat equations. So kinematics is all about the mathematics of things that are sort of moving. And specifically we tend to use Suvat equations for this. In this case, we're going to be looking at combining our knowledge of vectors with Suvat equations, because as you know, when you're thinking about Suvat equations, you're usually thinking about stuff that's moving in a line. So it might be a diagonal line or horizontal or vertical, but it's still a straight line. Whereas with vectors, we can do things in 2 dimensions or even maybe 3 dimensions. So that's what we're going to be looking at today, combining vectors with our knowledge of kinematics. So let's start with the fundamentals. You remember speed equals distance over time, right? So let's just write that formally here, speed. So starting nice and simple, speed equals distance over time. And then of course, you could alternatively write that. So this double arrowhead means it's equivalent. That's the same thing as saying distance equals speed times time. Okay, so hopefully with me so far. Now, when we say, distance equals speed times time, this distance, what we really mean is the distance from where you first started, right? So let me give you a specific example. So let's say my speed was 10 meters per second, and I did that for 5 seconds. Okay, how far would I have gone? Answer's just 50, right? I've gone 50 meters. Now, what if I said, well, I didn't actually start at a 0 point. I didn't start at 0 meters. Let's say I was already 10 meters away from somewhere. I was already 10 meters away. So let's say initial distance is 10. Okay. So 10 meters away from somewhere. It's how I'm measuring distance. You always measure distance with respect to a point, right? So I'm 10 meters away from somewhere, and then I say I continue running at 10 meters a second for 5 seconds. What is my current distance? So now it won't be 50, right? It'll be 60. Because I started at 10, and then I traveled 50 more, and now it's 60 meters, right? Hopefully with me so far. So now we can modify this little expression slightly and say distance is actually equal to initial distance, and I suppose really this distance here, let's call this final distance. So your final distance is equal to your initial distance plus the speed times time. Okay, so all this we've basically just got from the speed equals distance over time equation, right? Right, so that's it. Final distance equals that. Now, we want to turn this into a sort of vector equation. So this is how you usually see it written in vector form. Okay. The initial distance we tend to write as r and then 0. That little 0, it kind of means at 0 time. So when no time has passed, at the 0 time, what is your distance? And in that case we use r subscript 0. This is partly to do with the fact that for distances we tend to use s or we tend to use r, and we kind of use them interchangeably. And when we go to vectors, we tend to favour the letter r. Don't ask why, it is just an arbitrary decision which letters we ended up using. But for vectors, we tend to use the letter R to represent distance. So for initial distance, we'll call it R0. Then for speed, or in other words velocity, we can just use V. And time, we can go with our old favourite T. And all of that is equal to final distance, which we can then just call R. So R0 is your initial distance, and then R is your actual final distance. And all of these are vectors except for T. Remember, T is a scalar. Okay, so this is our useful formula. Okay, R equals R0 plus VT, and you'll see it in the book as well. So what this tells us is if I have an initial distance or initial position, I could say plus velocity times time, it gives me my final distance. In fact, I think more accurately, I'm going to change this word distance to position, because I think you tend to see that wording more. Okay. Final position equals initial position plus speed times time. Okay, so let's apply this formula to an example. Okay, a particle starts from the point with position vector 3i plus 7j and moves with constant velocity 2i minus j. Find the position vector of the particle 4 seconds later. Okay, not too bad. Let's label these things accordingly. So this thing, 3i plus 7j, what is that in this context? That's the start position. So it's a position vector, and it's where it first starts. So this thing is R0. That's our R0, the start position. Constant velocity 2i minus j, that's our v. And in the case of part A, we've got t here, that's the 4 seconds. So that should be enough information, right? So for part A, I'm going to write R is equal to R0, which is 3i plus 7j. I'm going to write that as a column vector. And then add to that the velocity times time. Let's do it time times velocity. It looks a bit neater. So time is 4 seconds, times the velocity vector is 2i minus j. So that's 2 minus 1. Okay, and then we can work this out. So that's 3, 7. Again, plus 4 times 2 is 8. 4 times minus 1 is minus 4. And now we can add those two vectors together. We get 11 and 3. And that's it. And we could maybe also just then say that's 11i plus 3j in case they want it in that form. Cool, so that's part A done. Not too bad, just using this formula. Let's have a look at part B. Find the time at which the particle is due east of the origin. Okay, so in order to do this, we need to remind ourselves, we've got to be quite specific about what it means when it's saying due east. And in other questions, it might say, give you something else like, you know, due north, due south, and so on. Let me just draw out a little compass. Okay, so you've got your northeast, southwest. Now, if a vector is due east, it means it's perfectly horizontal. What can I say about its position vector? What will be, so it's two values, right? It's an x and a y. The top one, what are we thinking its x value must be? If something's perfectly due east. Hopefully it's, oh sorry, I should rephrase that the other way around. What should its y value be? Yeah, what should its y value be? So it should be 0. Okay, because this vector here is only going horizontally, only along the x-axis or the I direction, and it's going not vertically in any way at all. So no j component at all. So therefore it's something 0. That's as much as we can say. In the case of north, it will be 0 something. In the case of west, again it'll be something 0, and again here at south it will be 0 something. Okay, so just to be clear, this has nothing to do, this is not me answering the question yet, this is an aside. I'm just considering, what does it mean when somebody tells me a vector is due east or due north? What it really means is it's in this form, this blue form. So if I told you I've got a vector, it's going west, it's due west, what you know then is, the j component must be 0. That's what you know. Okay, and similarly for east, the j component must be 0. And I suppose, what do we know about the question mark? It must be positive, right, because it's going to the right, which may be useful. So, for part B, we know the j component is 0. So let's make a note of that. If it's due east, the j component is 0. So, at what time will the particle be due east of the origin? Okay. So what we're going to do now is we're going to say, okay, r is equal to, now let's put again r0 37 plus, now I don't know what t is, so I'm just going to keep it as t, times the velocity 2 minus 1. Now what I'm going to do is I'm just going to combine this into a single vector while keeping the t's there. So this becomes 3 plus 2t and 7 minus t. And then what we're saying basically is this is a formula. This is a formula for r in terms of t. So when t is 0, r is 3, 7. Makes sense. That's the initial position. When t is 1, r is 5, 6. And the question is, what value of t makes it so that the j component is 0? So when is this equal to 0? Well, it's when t equals 7. And that's it. That's answered the question. When t equals 7, that is when the particle is due east. So it's not too difficult in that sense. Cool. Okay, so what we're going to look at now is the vector version of the Suvat equations. And hopefully you'll be quite happy about this because they're basically exactly the same, except all you're doing is the quantities that have become vectors, you treat them as vectors. And the quantities that are still scalars, you just continue to treat them as scalars. So, let's see. I'm going to write 2 of the key Suvat equations and we'll see what the vector version looks like. So, let's write here's the standard Suvat equation. Okay, so this is standard Suvat. And let's go for the 2 that we're going to be using soon. V equals u plus at and s equals ut plus a half at squared. And now let's write the vector version. Okay, so all we have to do is consider which of these quantities in the equation can we turn into vectors. So v is velocity. In 1 dimension it's just a positive or negative number, but in 2 dimensions it can be a vector. So yeah, I'm going to change that into v as a vector, just put a line underneath. Equals initial velocity, same story, also a vector, plus acceleration, also a vector, can be written as one, times time. Time can't be a vector. Time is just a value. It's a certain number of seconds or hours or how we're measuring it. So that's t. And that's it. That's the vector version of that Suvat equation. Then if we look at this one, similarly, distance can be a vector. Initial velocity, vector, times time is not a vector. plus a half, that's just a constant, times a is a vector, times t squared, definitely not a vector. Which makes sense as well, right? Because if you ever have something squared, it can't be a vector. You can't square a vector. I mean, maybe at university level maths, you might be able to give some meaning to squaring a vector. But, you know, the bog standard definition of squaring, which is to multiply something by itself, you can't do that with vectors. You can't times vectors together, not in the usual sense. So, definitely a scalar, that t. Now, like I said, there is a bit of funniness with the names of the quantities. For whatever reason, when we go over to vectors, instead of calling it s, we call it r, which I mentioned before is sort of your position or your distance. Again, who knows why? It's just that we ended up with two letters describing the same quantity, and the standard convention is that for one-dimensional situations, you call your distance or position s, and for vectors, you call it r. But they are representing the same thing, really. Whereas the other letters don't change. And that's it. That's your vector version of the Suvat equation there. So perhaps for the other two equations, or other three Suvat equations, you can probably see the same sort of pattern going on. Okay? Cool. All right, so let's make use of these then. So we've got two examples, then I'll give you some questions. So we've got a particle p, velocity of that vector at time t equals 0. The particle moves with constant acceleration, this. Remember, constant acceleration, therefore we're going to be using Suvat. Find the speed of the particle and the bearing on which it is travelling at time t equals 3 seconds. Okay. So let's break down all the information into some sort of mathematical notation. At time t equals 0, this is the velocity. So in other words, the initial velocity, that's time t equals 0, equals minus 3, 1. That's the minus 3i plus j. Okay. The particle moves with constant acceleration, this. So that's easy peasy. A is equal to 2, 3. Find the speed of the particle and the bearing on which it is travelling at time t equals 3 seconds. Okay, so at time t equals 3, I now want to know what is v, the vector. Okay, so let's use our Suvat equation. V equals u plus at. I strongly recommend getting in the habit of doing the little line for vectors. It doesn't take that long, and I think what it does is it makes you very aware of which letters represent vectors and which letters represent scalars. If you don't get in that habit, you lose the advantage of having an extra tool that lets you spot errors. So for example, if you see two vectors being multiplied, you know that makes no sense, I've made a mistake. So it's really useful to keep track of which things are vectors. So we've got v equals u plus at. Let's work it out then. This is equal to minus 3, 1 plus t is 3 times 2, 3 equals, that should be a 6, and that's equal to 3, 10. Should be 310. Got that right? Great, so that is the velocity, v. Now we've got to be careful because technically the question said find the speed of the particle. So speed, remember, means I'm actually finding the magnitude of v. So what I want, speed, is equal to the magnitude or size of that v vector, and that's going to be equal to the magnitude of this 310 vector, which hopefully you remember is just root of the sum of the squares of the components. So I root the sum of the squares of the components and I get square root of 109, which equals roughly 10.44 meters per second. Sorry, 10.4. Okay, and that's your answer. We've done it. Okay, so it's quite nice, really. It's going back to sort of more basic SUVAT style questions. You just have vectors now, and you just use the usual rules of vectors. The other thing we need to do still is get this bearing. So in order to do that, let's just clear some space. We know now that it's the vector 310. Let's keep that there. So it's the vector 310, and you're doing your usual trick, or not trick, but method, where you go 3 along, say, and then 10 up, and then you're just going to be finding the bearings using a bit of trig. So remember, technically, if I want a bearing, it's a little bit irritating, this convention, but if I want a bearing, it means from north clockwise. What is this? So what I'm actually going to do is find, well, there's several ways you could do it, I suppose. Perhaps the easiest really is to create a new triangle. We'll say that's 3, which it must be. This is 10. And therefore theta is equal to tan inverse of opposite over adjacent. So that's 3 over 10. Okay, so tan inverse of 3 over 10, check that on the calculator, should be 16.7 degrees. So therefore my bearing, if we want to use the convention of a bearing, it needs to be 3 digits and rounded up to the nearest whole number. So 16.7, that rounds to 17. So I'm going to write it as 0.17 degrees. Okay, and that's the bearing. Cool, let's look at one last example. Okay, let's see how quickly we can do this one now. Ice skater. Skating on a large flat ice rink. At time t equals 0, the skater is at fixed point O. It's just saying she starts at distance 0, which is good, and is travelling with this velocity. So therefore, we have that u, initial velocity, is equal to 2.4 minus 0.6. At time t equals 20, the skater is travelling with velocity minus 5.6, 3.4. Okay. Relative to O, the skater has position vector S at time t seconds. Irritatingly now, they've decided to use S instead of R, which is less common. So just remember, S and R, they're really the same thing. Usually, they're treated as the same thing. They're just the position vector. Modelling the ice skater as a particle with constant acceleration. Okay, so we know the acceleration is constant. So now find the acceleration of the ice skater. Right. So the acceleration is constant. We don't know what it is. Let's use the information that after 20 seconds, t equals 20, the final velocity, v, was equal to minus 5.6, 3.4. And then we can do v equals u plus at. And let's do a bit of vector rearrangement actually, because what we can turn this into is v minus u equals a times t, which it can then be turned into a equals v minus u all over t. That's completely valid. Which is what? V is minus 5.6, 3.4. U is 2.4 minus 0.6. And then we're going to divide that whole thing. So all the components will be divided by 20. And what do we end up getting for that? Let's write it up here. Maybe double check it with me. And you should get minus 0.4, 0.2. Okay, and that's our acceleration. Great, okay, we can remove this working now then. Yeah, let's get rid of all of it. And now let's look at part B. We want an expression for S in terms of t. So again, they've swapped S for R in this case, but it all ends up being the same thing. We've got the formula S equals UT plus a half AT squared. Okay, that's my U. And the A we've just worked out. U we've already been given. What was U? It was 2.4 minus 0.6. So we put that in there. We've got the acceleration, so we're going to add half of that. Now if A is minus 0.4, 0.2, then a half of A is, of course, this. Halving all components, so let's stick that in here. Minus 0.2, 0.1 times t squared. Cool. And now we can combine these two vectors by combining the top and bottom rows. So for the top row, the I component, I'm going to take 2.4t and then minus 0.2t squared. And then for the bottom row, I'm going to take minus 0.6t plus 0.1t squared. Okay, and that's our vector. That's our value for S. Let's plug that in here as our final sort of statement. And it looks a bit complicated, but it makes sense. If you can always check. If I plug in 0, what happens? If I plug in 0, I get 0 everywhere. In other words, at time 0, it starts at the position 0, 0, which makes sense. That's the origin, right? And then at time 1, you can put in t equals 1, and you'll get a value, a vector, which is the new position at time t equals 1. And you can find out wherever this skater is at any point you like, just plug in the appropriate value of t. Okay. Now, part C, interesting question. It asks, when is the skater directly northeast? So we talked about northeast, southwest. What about something like northeast? So if I draw the compass again, okay, so we've got our north, our east, and northeast is of course this direction. What is special about all of the positions? Because, you know, this skater, I mean, she could be anywhere along this yellow line, right, northeast. Any of these points could be the skater. So what is special about those points compared to, say, the points here or the points here? To relating their I and j components. So let's say, for example, this is position 4, and I mark on the line the position with I component 4. What would the j component be? It's also going to be 4, right? The j component. So to be northeast means your I and j components of your position vector are equal. Right, so let's make a note of that. This is saying that the I and j components are exactly equal. They're exactly the same. Right, so let's then apply that mathematically. So we're going to have the I component, which is minus 2.4t minus 0.2t squared. That's equal to the j component, which is minus 0.6t plus 0.1t squared. And now we've basically got a quadratic equation, right? We just need to rearrange, make it equal to 0, and we've got a quadratic equation. So it becomes 0.3t squared. What do we get next? This minus shouldn't be here, sorry about that. 0.3t squared minus 3t is equal to 0. I think that makes sense. And then the value for t, you get two solutions with quadratic quite often, right? It's rare that it's exactly 1. If you're going to have solutions, it's usually 2. In this case, one of the solutions is just 0, right? which is kind of an invalid solution, because to say I'm at 0, 0 and therefore I'm northeast, it doesn't really make sense. It's kind of like saying when you're at the North Pole, are you north? I mean, you're sort of in every direction in some sense. So we're going to ignore the t equals 0 solution. So implies when t is not 0, what does this equation become? Well, let's divide by t everywhere. So I'll get 0.3t minus 3 equals, and then 0 divided by t is still just 0. And now we can solve this quite easily, because this is 0.3t equals 3. 3 divided by 0.3, and what do we get? 10. And that's our answer, at t equals 10. So that's it. T equals 10. She's northeast. Perfect. Okay, and then final part. A second skater travels and has position vector 1.1t minus 6. Show that the two skaters will meet. Right, so let's make a note of these two skaters. So let's be nice and mathematical about this. Let's say skater 1, and put a subscript here, is that. And skater 2, it's a coincidence that the S happens to begin with skater, but S2 is, right, okay, at time t, right, equals 1.1 t. We've got to be careful here. Right, a couple of things. First of all, they've used R. It's the same as S, right? They're just being a bit annoying and trying to trick you by saying here we're talking about S and here we're talking R. Notice it says here position vector S, and here it says position vector R. It's the same thing. So I've done S1, S2. You could also say S and R. It doesn't matter. The second trick here is notice there's a J component, but there's no I. So they've implicitly told us this is 0, and then the next part is the J component. That's 1.1t minus 6. Right. Question is, do they meet? What does it mean for two things to meet? I mean, what does that mean? If two things meet, it means they're in the same place at the same time. Right? It seems kind of obvious, but two things have to be same place, same time. So mathematically, what we want to know is there a value of t which, if I substitute it into both of these expressions, I'll get exactly the same values. So I'll get the same I component, the same J component. The way we're going to do this is to be a bit clever and think, okay, for these vectors, the only vector which has a component that never changes is this one here, S2. This I component never changes. So that must mean that if they are going to meet, then the I component has to be 0 for the S1. So what value of t is that? What value of t makes this equal to 0? So let's do that first. So let's take 2.4t minus 0.2t squared and say it's equal to 0, because I'm equating the first row, the I component here, with that one. And it happens when, so either t equals 0, or we take out the t factor. So we divide by t, we get 2.4 minus 0.2t equals 0, which implies, what do we have? 0.2t equals 2.4. So therefore, t equals 12 in that case. Right, but we're not done yet. So what we've done is, these are the only two possibilities. If they're going to meet, it has to be the case that t equals 0 or t equals 12. If they do meet. They might not meet though. We still need to prove it. So let's try 0. Does it work? If I put 0 into this bottom row now, I get 0. And if I put it into this bottom row here, I get minus 6. Doesn't work. Okay, so at t equals 0, they don't meet. And then let's try the t equals 12. For the top row, well, we know they're going to be equal, because that's how we got t equals 12, right? So this is going to be 0 when t is 12. So is that equal? And then what about the bottom? So let's check. When t, let's do this one first. At t equals 12, what do we get? 1.1 times 12 minus 6. I get 7.2. Let's say j equals 7.2. And then for this one, at t equals 12, what's the j component? Minus 0.6 times 12 plus 0.1 times 12 squared. 7.2 again. Okay, so it worked. They're going to meet. So in this case, t equals 12, the two skaters definitely meet. Their position vectors are the same. Cool, all right, that's it. So that's your sort of initial intro into kinematics using vectors. Hopefully it made sense. You can use all the Suvat equations you've wanted, the ones you've used before. You're just using them with vectors now. Okay, so some questions for you to try. They're much shorter questions than ones you've been doing recently. Less diagrams, more just mathematical expressions and calculation. So see how you do with these, starting off simple. Right, so here's your first question. I won't give you a hint, just see if you can do it. Pause the video now. Okay, and there's your answer. Okay, and just two more questions. Let's try this one. When you're ready, pause the video now. And your answer. And let's look at our final question. This time we're looking at when something collides. So remember, for two things to collide, their two position vectors are the same for the same time. Same place, same time. That's what it means for things to collide. You can give that a go. Pause the video now. Okay, and there's your answer.